Okay, so we just saw until here that how we can prove convexity of sets, how we can prove convexity of function. We saw that the epigraph of a function is if you prove that the epigraph of a function is convex, then the function itself is convex, and inversely, it's equivalent. We prove that if S1 and S2 are convex, that the intersection of both are convex. We saw about this property of uh, local minima or all global minima in convex optimization, which makes convex optimization a really good tool. We saw also like three main conditions about convex optimization from the theory, like can the problem be bounded? Uh, if bounded, can it be solvable? And yeah, so and can we actually solve the problem? Like if bounded is the optimal value achievable, and can you actually solve the problem? And we solve the gradient equation for proving convexity and also using the epigraph for doing it. And so now I want to go more into concrete stuff and so the different families of convex optimization. So the first one I want you to talk to you about is linear programming. Maybe you can create like as open classroom, the open classroom of quantum. Yeah, it will be so cool because for now, it does not really work really well, I think. So about the platform for learning quantum. So a linear programming problem is defined by a triple CAB, where C is into r of the power of n, a being r. Well, anyway, fuck the definition. Here is the form. You just have this. So that's the simplest family of convex optimization because it's linear and so it's really easy. So if you remember in the last video, I just tell you that every program can be written as this. Well, more specifically as this. And so here you see in this family, in this linear programming family, which is the first family we're studying, like f of x is just C transpose x. And there we go, just after into infinite sub, like it's less or more the same in this case, that's why we can interpret them. And S here is equal to x being to the like this. Knowing that those two conditions. So all the family we're studying, we respect this, but with some constraints on it. So that's just this linear programming. It just is general form with those constraints. So that's it. So it's very easy to check that S is convex set directly, and in fact, like the intersection of a collection of half spaces, which by lemma one must be convex. And so maybe I'll prove it into a next video. And yeah, the simplicity of linear programming comes from the fact that the variable x appears linearly everywhere, here and here, and and yeah, both in the objective value and in the constraints of the problem. Um, and maybe about minimization or maximization, like the way we try to minimize and here to maximize. Like for a program to be a convex optimization problem, we need the objective function to be convex if we're minimizing, or concave if we're minimizing. So convex if you're minimizing. So here, like this, and concave here have like this. And so yeah, but when the objective function is affine, we can both minimize or maximize. So in this case, because it's affine, both can work. Um, and so not like here, as I told you, we choose to define only the maximization of the definition. But this is actually sufficient to convert to the case of minimization. This we can transform it in inf simply by doing min of f of x. It's just equal to minus max minus f of x. And so here, for example, we had, so if I want to transform this in a mean, um, it will be like inf of x being into r of m minus c transpose x such that ax is inferior to b and x is superior to 0. So hence we can always restate the minimization problem as a maximization problem. But the problem at the end will be the same Mathematically, like it's okay, but like the x will be the same, so you can just write it like this. And you don't need the minus before. Like mathematically, it's more rigorous to write it, but for the optimization on itself, you can directly write this and do not need this minus before, because at the end it will be, if you're trying to have the concrete value, it will not really change. Instead, here we write it like this, and here indeed I write it more like this, and it's less rigorously mathematically true, but it works for concrete stuff. And it's more often how it is presented on the books. I mean, if it is as if you have something like this, and there is 0 here, there's minus 10 here, or let's take, no, it's minus 10x, it will be more pedagogical. Here it's x, and here is 10x. And so no matter if you're searching here, or if you're searching here, at the end, you'll know what this is. So that's the same stuff about those two stuff. And most of the time they write it like this, even if normally, mathematically, in the definition, it is written like this. You can directly skip it and write it like this, because at the end it's the same to search this or this for finding x.